Good morning, good evening, good afternoon, wherever you are. My name is Vishnu Dutt, and today we will be talking about question number 13 of Network Interview Preparation Series. Today's question is going to be really interesting, just like other question in the series, as this question is asked in many network interviews. The question is simple. Tell me whether OSPF is a link state routing protocol or distance vector. And you must be wondering, Mr. Vishnu, this question is really easy. OSPF is actually link state routing protocol, and I do agree with you. But believe me, OSPF is a link state protocol inside a particular area. But when we talk about between areas, it behaves like a distance vector. If you don't get it, that is fine. We will be talking about this thing in some design as when we discuss some design aspects of OSPF. But today we will be talking more about link state perspective of OSPF. And if OSPF is a routing protocol which is based on link state, then how it avoids loops in network. Believe me, loop is a major problem in the network. I have just one agenda today to explain you the link state nature of OSPF and how it avoids loops in the network. If you are with me, let's move to the first board to discuss then in great detail.
We have one orange subnet here, we have a green subnet here, and you can see that basically in the orange subnet we have 192.168.10.0/25, which is actually 128 host network, and router R1 has link in it. So maybe it is going to be the default gateway for this network, right? Similarly, we have 172.16.10.0 here, and R3 has a link in it. And of course, this link has the first IP address because generally we configure first IP address of this network onto this link. Pretty simple, right? Now, just try to understand that we have four routers and we have white color links between them. This one, and again, these links are configured with network value, right? For the simplicity, I have mentioned here that everything is /24, right? If everything is /24, then you understand that there are 256 hosts over this link, although we know that there are only two routers. But for the simplicity's sake, I have put this as /24 to make you understand that it is not the case that we have only orange subnet and green subnet. We actually have four more subnets between these routers. And that subnet is the first subnet is 10.1.12.0 between R1 and R2. And whenever you create your lab, right, if you want to, and you should be, so please make sure that whatever the IP addressing scheme you are using here, right, it makes sense. For example, in this addressing scheme, if I talk about this network, which is 10.1.34.0, so I have made sure that the third octet has some meaning in it, right? And what is the meaning here? The meaning here is 34. It is the link between router number 3 and router number 4. So irrespective of the fact you are watching this, you are seeing this IP address, you can straight away draw a conclusion that 10.34.0 means it is a network between 3 and 4 router. It is as simple as that. So this was little bit information about this topology, which you all know. So now we are going to again talk about how actually how link state routing protocols are different approaches compared to distance vector. Although we had a discussion yesterday also, but here I will be showcasing you what exactly going into these routers mind and what exactly they do, right, when we run link state routing protocols over them. So here we are having four routers, and what we have configured is I have configured a routing protocol with the name L over all the links on these routers, right? And the standard property of this link language or routing protocol L is that it is link state routing protocol. As soon as I run this link state routing protocol on R1, right? What goes in R1 mind? What is the approach of R1? We are going to discuss this. So actually, as soon as I enable link state routing protocol on R1, it starts thinking and it starts uh, creating some information regarding its network and the links, and it is going to pass it along, right? In this case, first thing first, R1 tries to find its neighbor, right? And I have given you the standard definition of the neighbor, that whatever is connected over my own link here, right? That is my neighbor. I haven't discussed how R1 is going to find out that R2 is R2 its neighbor, or how R2 is going to find out R1 is its neighbor. And believe me, we are going to discuss this in detail because this is one of the important step when we are going to discuss OSPF, right? And that is exactly where we are going to talk about hello protocols. Through hello, R1 and R2 comes to know about that they are neighbor of each other, right? So first thing first, they know the neighbor, and now just try to understand what is going inside a router R1 mind. It is creating an information, right? A packet in which it writes few things, right? What exactly it is writing? Just what exactly it is writing? It is saying I am R1. It means that it is identifying itself, right? Right now, here I am saying I am R1, and that is basically unique across this complete topology, right? You can argue with me that what if it is going to happen that if somebody has configured another router with the name R1, so I am saying this thing should be unique, right? Maybe an IP address you can configure here which is unique, which we also call the router ID, right? But try to understand from a high level point of view that R1 is thinking and creating this message, yellow message, and inside this yellow message it is going to write I am R1 and I have two connected links. Interesting, right? Which it is that one connected link is into this orange network and the another connected link is right here. And it is also informing that my neighbor is R2. I haven't discussed till yet how to find the neighbor, but try to assume this that R1 knows now that R2 is its neighbor, which is over 10.1.12.0 link, right? And absolutely, over this orange network, we do not have any neighbor because we do not have any router there which is running this language L or this link state routing protocol. What is the definition of neighbor? I'm again speaking, it should be on my same link and it should be running the same routing protocol which I am running, right? And R1's from R1's perspective, R2 is fulfilling its condition because it is connected over this link and it is running the same routing protocol. So again, I'm repeating, R1 is creating a message in which it is writing that I am R1 and connected with two network links, right? And my neighbor is R2 over 10.1.12.0/24 network. It is as simple as that. It has created this information, it has put this information right here into this message, right? Which we are calling message M, or actually in the real terminology, we call this message as link state advertisement. What is the meaning of it? The meaning is I'm advertising all of my links, right, to my neighbor. And that is why I am calling this link state advertisements. As simple as that. And one important thing is that basically we are including the cost too. What is the meaning of it? Yesterday, when we were discussing the example of cities and houses, right? We mentioned that between two cities, we have a number here, and that there the number was kilometers, right? And we could find out the distance between cities on the basis of different paths and which path has the shortest number of kilometers so that we have the best path to reach to that city, right? We discussed about it. The whole sole point was that if we have a complete picture of the network, we can do that, and that is what we are trying to build, a complete picture of the network. You can argue with me, Vishnu, that I can see the complete picture. Now the question is not you. The question is that whether every router can create the same picture, right? In the case of distance vector approach, it was not possible at all. Why? Because if I draw 3 or 4 routers, this router was informing everything to this router. This router was creating the routing table, creating the best route, and then informing others, right? It means that this guy was totally dependent on the routing information from the middle guy, and it could be wrong, right? You will be finding some important thing which are quite similar to the distance vector approach, but believe me, guys, approach is totally different, and that is the main point of drawing this board, building this board, so that you can understand and pretty sure about the difference, right? Along with that, R1 is saying the cost is 10. What is the meaning the cost is 10? It is saying, and basically on whatever link it is going to advertise this, right? It is going to introduce the cost of that link, right? On what basis? What are the nitty-gritties associated with cost? We don't know till yet, right? And believe me, we are going to discuss it in detail. But overall, how it is working, it is including the cost. It means that it is including this cost, right? And suppose this is 10. What is the meaning of it? The meaning is that if R2 wants to reach to R1, this number is 10. So if I draw this picture, R1 and R2, this number is 10. It is as good as number of kilometers. And if this number is less between the routers, then basically we are talking about the shortest path, just like the number of kilometers between the cities, right? So for now, I have in this diagram, I am saying that all the cost is 10, right? So every link, whatever we are seeing here, is having cost 10, and we are advertising only the cost into this LSA or the message, whatever the cost of this link, wherever I am advertising the message, right? Or I am advertising the LSA. So it has created this LSA, link state advertisement, this router R1, right? And what is written inside it? I am R1. I have two links, right? I have one neighbor over the one link, which is R2, and my cost is 10, right? It is advertising this LSA towards R2 because it is the neighbor, right? And what is this LSA? Obviously, this is the LSA for R1. As I mentioned, then that in link state protocol, R2 is not going to do any computation on this LSA. It is just installing this LSA into its routing table where it is going to say that this LSA is from R1. It is just taking it from the neighbor. It is installing into the database. Nothing else, guys. And this is the huge difference. Here, basically, we are calculating the best path and then we are advertising the best path to the another router in distance vector approach. And you can understand the timing difference. Maybe when you do the calculation in the intermediate routers, maybe, suppose as a hypothetical example, it is going to take 2 seconds. Suppose right now, right here, R2 is not doing anything. Whatever the LSA is forwarded by R1 or it is receiving from R1, it is just putting it into the database and then forwarding it everywhere, right? Simple. It means that R3 is going to receive this LSA in no times. And suppose in distance vector, every router take 2 seconds for the computation. Here, you are not doing anything. You are taking the packet, putting it into the database. This is not the routing table. This is the database, for example, database of router R2, right? And then it is sending it. So maybe if you are talking about 2 second in distance vector routing protocol, R2 is not taking any time. Maybe it is taking time in milliseconds, right? And that is why these protocols are fast. Okay. Now, fast in terms of how much quickly this LSA from R1 can reach to R4, it depends basically on your, actually it is going to be the same as whatever an IP packet can take from R1 to R4 because every middle router, whatever it is seeing the message, it is putting the message into the database and sending it, right? So the message or the routing information flow happens at the speed of the packet. If you consider a normal IP packet, whatever it takes from R1 to R4, the same it is going to taken by this LSAs or link state information, right? What is going to happen at R3? R3 has its own database. It is going to put this routers R1, this is LSA into its database. Similarly, R4 is going to put this LSA here, right? You can argue with me that Mr. Vishnu, won't R4 is going to announce it here? And won't R3 is going to announce it here? Absolutely they are. But when R4 sees that it has already this LSA, then basically it is not going to install whatever is coming from R3, right? As simple as that. Okay. So now let's talk about these are the database which we have created till yet. Now let's think from the perspective of R2, what is going to happen there, right? R2 has three links connected, link this one, and this one. And exactly this is what it is saying that I am R2, I am going to create an LSA now, which is for me, I am R2, and it is saying I am connected with three network links, which you can see, right? It is connected to three different networks over this links, right? And it has calculated that it has neighbors R1, R3, and R4. Of course, R2 is not the neighbor because R2 is this router itself. So it is saying my neighbor is R1, R3, and R4 on different links. So on R choose this link, right? Maybe it's a 0/1. We have 10.1.12.0 network and we have connectivity to R1, right? Which is its neighbor. Similarly, over this link, if I draw from red pen, this link, we have a neighbor of R2, which is R3. Similarly, over this link, we have neighbor of R2, which is R4. So it is saying I have three links. I want to advertise them. And it is also advertising what are the neighbors associated with them, right? As simple as that. Now the cost is again 10, so it is saying that everything is 10, 10, 10. It's perfect, no issues. And now what is going to happen whenever it creates this information? It is going to forward this information towards R1, towards R3, and towards R4. What is going to happen at R3, guys? It was creating its database here, right here. It is going to include this information also from R2, and then it continue forwarding it. So we have another LSA into the database. Here also we have another database, which is R2. It is as simple as that. And now R1 is also going to create its database where it will be putting the R2, right? As simple as that. Similarly, R3 is going to advertise its LSA in which it is going to say, I am R3 and connected with two network links. Which one? This one and this one. And of course, on these links, we have R2 and R4 as a neighbor. And again, it is saying the cost is 10. So cost actually, I have taken 10 for everybody because I see that these links are same. If that is the case, then R3 is going to advertise it towards R2. R2 is going to put this thing into its routing table, means R3. It is as simple as that, right? It is going to put this thing into its routing table and continue forwarding from here and here also. And R1 is going to see this again, means R3. Just try to think what I'm trying to build here. Again, when R4 does the same thing, it is going to be here into R3's database, into R2's database, and into R1's database within no time, right? Because it is going to go from the speed of packet because no middle router is doing any computation, but they are just building the database, right? And of course, R1 knows about itself, right? R2 also know about itself and whatever the links connected. R3 knows about itself, so this information is also there in the database, right? R3, R1, R2, and R4. Absolutely right. Now try to think. Do you see some common pattern here? Every router's database is exactly the same, right? Because every router's database contains what? The information from other router, which is forwarded by in the in-middle router, which are eventually storing that information in the database, right? R1 announced something, R2 stored it, forwarded towards R3, R4. And that is the reason that every router, if we use this approach, is going to have exactly same database, which you can see right here, right? But you must be thinking that is fine, Mr. Vishnu. You have created the database. What is the use of it? And believe me, if you understand this, that every router has the same perspective of the network, then actually every router is capable of drawing this or visualize this, that how my complete networks look. It was not the case with distance vector routing protocol, because in distance vector routing protocol you were totally dependent on your neighbor. Whatever your neighbor is saying, you are saying okay, that is true. But now you are not, you are dependent on the neighbor, right, just to forward those link states. But when these link states are into your database, right, from every router, you are pretty sure that now I can visualize this network. How? Let's see this in the next board, which is right here. And believe me, if you can understand this board, you you understand the overall philosophy of OSPF protocol, because we are talking about here, we are talking about link state routing protocol, right? Which are which is a slightly different approach, right? So if you understand this, you understand the philosophy behind OSPF protocol. So just try to concentrate more here. If you are not able to read the below diagram, that is perfectly fine, because this is exactly what I discussed in the last board. But I have mentioned this diagram here so that you can understand that we are talking about this diagram, and this whatever the information we have collected into these databases of R1, database of R2, database of R3, which were absolutely same at the end, what magic we can do, what magic these every router can do. But please have this information in your mind that if we have cities connected with the houses, right? Then we can computer science through computer science and basically its various algorithm, which includes Dijkstra's algorithm. We can always calculate the shortest path between these houses or between these cities, right? On the basis of number of kilometers. So if somebody can give me this picture of city and houses, I can sit around and I can calculate the shortest path. Similarly, computers can or routers can calculate the shortest path, but the whole sole point is this picture should be there. Right now, I can see the entire network because the topology in front of me, but routers are not humans, right? If we want to explain that there is a complete picture, I just cannot click the picture and give it to the router. Router is not going to understand it, right? We need to explain routers all this thing in which language they understand. And basically, that language is the database. We are collecting information from different routers. We are putting that information in database. And exactly this is that database, right? So I want to showcase you everything from R4's perspective. R4 is the router here, right? You can argue with me, why not from R1, R2, R3 perspective? I choose just R4, just like that, right? But will it make any difference? No, because now R4, R3, R2, and R4, everybody is having the same database. It means that everybody's perception of network is same. Everybody can visualize the network, and that visualization is going to be the same because they are visualizing the network on the basis of database, which is absolutely same across all the routers. And I am emphasizing this again and again. This is very, very important that all routers are going to have the same database after some time whenever they are done with exchanging this LSA information, right? So let's consider what is happening at this router R1 when it processes or when it collects all the information from R1, R2, and R3. What is going inside its mind? And if we are talking about the mind, we are talking about the control plane. And when we were discussing the control plane, we discussed about that. Of course, control plane has a routing table, right? But on what basis this routing table was built at the first place? It was built at the basis of routing information which we are getting from another routers. And guys, don't you think this is the routing information which we got from other routers? Absolutely. And basically this we call as a database. So routing table in link state routing protocol is going to be formed from this database. But how? In this database, what I have done, whatever router R1 sent the information, I am showcasing you router R4 database and try to think whatever R1 has sent, I just keep it here. What information R1 sent? It sent that I am router R1, which is the distinctive factor, which is right here. Let me choose the red man, which is right here, right? And it sends that it has two links. Absolutely, it has two links, right? One is 192.168.10.0/25, right? Which is the orange network, which you see here. And the another one is 10.1.12.0, which is the link between R1 and R2. And interestingly, over this link, we have a neighbor, but over the first network or the first link, we do not have the neighbor, right? We didn't have any neighbor inside this orange network. You can see that, right? It is as simple as that. And if we talk about the cost, then we are going to include the cost whenever we are advertising the link over this information over any link. So that is why I'm calling at this interface the cost is 10, or basically we can say, because this is also 10, so we can say this cost is 10. Actually, this is the distance between the cities, right, in terms of kilometers, and I'm calling this as a cost here, right? As simple as that. Similarly, we talk about R2. So with this information, what R4 is thinking, right? R4 is thinking that somewhere, I don't know where, R1 is there, right? There is a router in my complete picture because I got a I got information from it. So we are thinking from R4's perspective what R4 mind is saying, and we are drawing it, right? So whatever the routing information is here in the database, we are going to draw it, right? Exactly. And you will be amazed to see that you can draw it, right? Now just forget about the below picture. Below picture is not there. There is no topology like it, right? Because from this, we have built this. From this complete picture, we have built this. And now from this database, we are going to build this picture, which is going to be pretty easy. Just try to think from this first routing information of router R1, what this R4 can deduce. It can say that there is a router, which is R1, because I got a message from it, which says that it has two links. One link actually doesn't have any neighbor, and here is the link associated with it, which is 192 something, right? And it is pretty sure that there is no neighbor over this link, because if it happened to be the case, then it should have written me here that there is a neighbor. So there is no neighbor there, right? And this guy has two links. One is into this network 192.168, and the other network is basically 10.1.12.0. And it is also saying that over this network, it has neighbor, which is R2. So I am just drawing this on the basis of whatever information I have, right? And it is saying the cost here is EPS10. Interesting, right? What is going to happen if we see router 2? It is going to understand that, of course, there is a router 2 also in my topology, which I get to know from the router 1 information or LSA also, which was saying it is my neighbor R2. So it came to know that R2 is there. But if I draw R2 independently, it is saying that it is connected with the three links, and all the three links are having the neighbors R1, R3, R4. R1 is absolutely here. It is going to draw R2 here. It is going to draw R3 here, and it is going to write down these networks and the cost here. As simple as that, right? So from R4 perspective, from starting to LSA from router 1 and LSA from router 2, it is going to create this R1, R2, R3, and R4, right? But still, the picture is not complete because we haven't talked about this network and the network, this network and the network between them. And yes, of course, because we haven't talked about R3 yet. Again, it is going to inform, I will get to, R4 is get to know that R3 is, there is any router R3, which is, of course, we have, because we get to know about from R2's LSA, and it is going to say it is connected with the three links. And of course, R3 is going to connect it with the three links, this one, and this one. This is the link which doesn't have any neighbors. So I have written it here, no. And over other link, it is R2 and R4, which I have drawn, right? And then I include the cost. And of course, R4 knows about itself that it is connected to R2 and R3, and here is the cost. It is very, very simple, guys, that from this database, you can totally deduce what should have been the network from which this database have been created, right? So I'm again repeating, we have this network. After LSAs, after creating the database, we created this database. And if I talk about it, then this database is as good as this network, right? Which I have drawn simplicity into, which I have drawn here, right here in a simple manner. It means that from R4's perspective, there are 4 routers in the topology, including me, right? I'm the R4. That there are R1, R2, and R3. How they are connected, I have drawn it. Absolutely, we have drawn it, right? And now, if we can draw it, and believe me, every router can do that, the same thing. Why? Because every router is going to have the same database. If we replace R4 with R1, R1 is going to have the same kind of picture. R2 is going to have the same kind of picture, because everywhere this is the database, right? As simple as that. And if that is the case, then every router can draw this picture into their memory, right? And if they can draw the picture, they can straight away run the previous algorithm which we talk about, right, in the houses and cities, that what is the minimum path from this R1 towards R3, which might be this one. From R1 to R2 is this one. From R1 to R4, it might be like this one, right? It can also calculate, of course, what is the path from R3 to R1, right? Which is this one, which we have already calculated, to R2, which is this one, which is the new one, and to R4, which is this one, right? So every router, doesn't matter if it can create this picture, it can create the shortest path from me to reach every other router. And if that is the case, if you can calculate this, then of course these two networks can talk, right? R1 can say that if it wants to reach 172.16.10.0, although there is only there are going to be two paths. One path is directly from here to here via R2. The other path is R1, R2, R4, R3, right? Which is going to be the bus path? You can calculate that pretty easily. How? Using the algorithm. And here the algorithm uses created by Mr. Dijkstra's, which we call Dijkstra's algorithm, right? So R1 can calculate then, and then on the basis of this picture or basis of this database, it can create its routing table in which it is going to say, R1 is going to say, if it wants to reach 172.16.10.10, now I have complete picture in my mind, and it is going to say I can reach it via R2. Believe me, just try to understand. It is not totally dependent on R2. R2 was just forwarding the LSA. This information is calculated by this router after analyzing the complete database that if it wants to send any packet towards 172.16.10.0, it has to forward it via R2 because otherwise there is no path because it can calculate to reach R3. The best path is R1, R2, and R3. It is as simple as that, right? Interesting. Slightly different approach, right? But it's a powerful approach. And that is why the possibility of loop is less here, right? And why? The reason is, suppose if R1 wants to talk to R3, right? And it has the complete picture, or suppose you are R1, can you somehow do this? That, okay, if I want to reach R3, I would like to go to R2, then I would like to go to R4, and then I would like to go to again R2, again R4, again R2, again R4. If you have a complete picture in your mind, can you come across this thing, which is a routing loop? No, no, absolutely no, because you know the complete picture. Why would on earth you are going to say, or why would you want to create a loop here, right? You can straight away go from here to here, right? Why there was loop in distance vector routing protocol? Because you are not sure whether your neighbor is correct or not, right? Most of the time the neighbor was correct, and that's why there was no loop. But what was happening there? You were totally dependent on your neighbor for the information, and if that information is wrong, that could have created that created the routing loop. But here the chances are less because you just not start working whenever whenever your neighbor is sending some information. You just put that into the database, you wait for some time, you make sure that everybody is having the same database, and then you start calculating, right? R1, R2, R3, R4 patiently wait for the routing information. Once they feel, once they think, once they are pretty sure that they have the same view of the network topology, they have the same database, then they start talking, then they start actually calculating the routes, the best routes, not before than that, right? But then what is going to happen if this link goes down, right? If this link goes down, then this information should be reached to everybody, and this information can reach again with the speed of the packet. For example, if this link goes down, R4 is going to generate this information, right? And if it is going to generate this information, then it is again going to forward this because there is a change in the information. It is going to forward it to here. R2 is going to again put this information into this LSA. It means into its database. It means the database got changed, right? And whenever the database gets changed, R2 need to recalculate its routing table. And it makes sense because the information gets changed, right? Similarly, R1 is going to get this update that previously whatever the R4 was saying, so it had the LSA in its database, and now it has generated another LSA. So maybe there are numbers that previously the number was 1, and now I'm getting it with the number 2. Then of course number 2 is more recent as compared to number 1. It is going to flush out this LSA and just include the new LSA. And if there is a change in the database, absolutely, if there is a change in the database, we need to calculate it once more time. But we need to make sure that every router is having the same database after this link change also. And that is not going to take much time. These updates are not going to take much time, right? All right, because when I say that we are talking about distance vector routing protocol, in middle router did the computation, and that is why the distance vector routing protocols are slow, because update reach to the 10th router, maybe if one router is taking 2 seconds, then it is going to take, reach there at 20 seconds after. But here the packet travels fast. It is coming here, it is flooding and flooding, as simple as that, right? Having said that, what are the steps which we discussed till now? Step number one, find neighbors. How? We don't know that. But the first step is find your neighbor, because you want to advertise your information, your routing information to your neighbors only, right? It means that you need to find them. The second thing is inform about your routing information or links to everybody, right? And this process is known as flooding, because you are flooding the complete topology with your information. R1 is going to say, I know with whatever link I am connected, and here is the information for you. R2 is going to send it to every other link, and we call it a flooding. We do not know till now when the flooding is going to be stopped, right? And there is a complete detail which we are going to discuss with respect to flooding also. Right now, I have give you the overall picture that how OSPF or any link state routing protocol work, what is the philosophy behind it, what is the logic behind it, right? But there are steps which we need to discuss. The first thing first, every router in the link state routing protocol has to find out the neighbors, right? The second thing is the flooding, because you need to flood routing information. Third thing is create this database and make sure this database is absolutely same across my topology. You can argue with me that, Mr. Vishnu, there might be 100 of routers which are connected, right? You are going to wait for that, and believe me, that is why we have the area, we have the concept of area. If you have heard about it, that we have area concept in OSPF. But if you don't know about it, that is perfectly fine. As a part of third step, we are creating the database which is common, which is going to be same across all the routers in my topology, right? And number four, because I haven't included, I haven't explained you the term area, that is why my last statement could be wrong, that the database is going to be same across topology, right? It should be inside an area, okay? But if you don't get it, that is perfectly fine. Step number four, once we have this database, what we are going to do on this database, we are going to run the algorithm, which we call as shortest path first algorithm, which is created by Mr. Dijkstra's, right? Simple four-step process. When you create the SPF, then basically you are creating your routing table. Once you have routing table, guys, this is the main goal of routing protocols, to create the routing table on every router, and that routing table should have the exact or the correct informations.